Okay, in this video, we're going to talk about the Rankine cycle and the efficiency associated with the Rankine cycles. So this is a diagram that you have seen in the class that represents the heat engine. So here you have a saturated liquid stream at high pressure entering the boiler. Due to the heat supplied from burning of fossil fuels, this liquid stream is converted into superheated vapor. The superheated stream then goes through the turbine, producing work. Note that this process is isentropic, since the entropy at state 3 is same as the entropy at state 2. So after the stream exits the turbine, it is mostly vapor, and very, very small fraction is liquid. That stream enters the condenser, is liquefied completely before it can enter the pump. The pump pressurizes the liquid stream to a high pressure, and this cycle can begin again. So what we want to do is compute the efficiency of this process. So efficiency is equal to net work that's produced by our cycle divided by heat supplied. So that's the efficiency, how we define efficiency for a heat engine. Our net work is work that's produced by the turbine minus the work that's consumed by the pump. So that's our net work coming out of the system. Then heat supplied is heat supplied to the boiler. That's QH. So let's compute three of these terms based on the previous cycle. So let's start with the work turbine. Work turbine is equal to, from the first law, H3 minus H2. Enthalpy here is 2800, from here 2800 minus 4000, that's equal to negative 1200 kilojoules per kilogram. Similarly, we can compute the work done by the pump. So that's H1 minus H4. H1 is 1000. H4 is 900 kilojoules per kilogram. That's equal to 100 kilojoules per kilogram. So note that our work done by the turbine is negative, and that is because our system is doing the work. And here work done by the pump is positive because the work is being done onto our system. Our QH is equal to H2 minus H1. H2 is 4000. H1 is 1000. That is 3000 kilojoules per kilogram. Now we have all three values that we needed to compute to calculate our efficiency. So we'll go back to our equation and substitute in these values. So work turbine was 1200 kilojoules per kilogram, work pump was 100, and our heat supplied was 3000. That's 1100 over 3000 equal to 36.7%. So that's the efficiency of the cycle. So now let's ask the question, what if our turbine was 80% efficient? So the efficiency we calculated, 36.7%, was assuming reversible turbine in an ideal case. But now the turbine is not ideal. In fact, it's only 80% efficient. So our efficiency equation remains the same. So work turbine minus work pump for QH. Again, so this is net work divided by heat supplied. What changes is the work done by the turbine. As you might have guessed, the work done by an actual turbine, actual turbine, is less than the work done by the reversible turbine. So the way I'm going to write it down is work done by the actual turbine is 0.8. The work done by the actual turbine divided by work done by the reversible turbine. That's about 80% or 0.8. So from that, work done by the actual turbine is equal to 0.8 times, so we computed the reversible turbine previously, and that was 1200, negative 1200, but since we have absolute values, I'm just going to write down 1200. That's equal to 960 kilojoules per kilogram. So it makes sense that work done by actual turbine is less than the work done by reversible turbine. So let's see how this updated value for turbine affects our exiting and input streams. So our input conditions to the turbine remains the same. The pressure is again 10 megapascal, enthalpy is 4000, and entropy is 7. However, our enthalpy value will no longer be 2800. And why is that? Because our work turbine is equal to 960. Work turbine is equal to H3 minus H2 is equal to 960. And I'll put negative values in there since the work turbine is negative. So our new H3 will be negative 960 plus H2. And our H2 is the same as before, it's 4000 kilojoules per kilogram, so that gives us 3040 kilojoules per kilogram. I'll write down here. Our entropy will no longer be isentropic, so our entropy in the initial state was 7. Entropy in the final state will be greater than 7. We don't have to compute that in this case, but we just note that since our turbines are not reversible, our process will no longer be isentropic. So I'm going to cross this out. This is not an ideal process. This is 80% efficient turbine. I'm going to go back and compute our efficiency for this process. The efficiency is work turbine is 960, our work pump is 100, same as before, and our heat supplied is 3000. So we calculate those numbers, our efficiency turns out to be 28.7%. Okay, so now let me ask this question. Is efficiency reversible that we computed to be 36.7%? 36.7%. Is that 0.8? If you multiply that 0.8, will that give you efficiency reversible? Just note, keep in mind that we computed that to be 28.7. The question is the efficiency of the reversible process simply 80% of the efficiency of the reversible process? If we multiply this 36.7 by 0.8, we get 29.36%, which is not the same as the efficiency of the reversible process. So the key point to emphasize here is that if our turbine efficiency is decreased to 80%, does not mean our overall cycle efficiency will be decreased by a factor of 80% as well. So our efficiency with a irreversible process is 28.7%. The efficiency for the reversible process is 36.7%. It's all from the